In this video, we will cover nuclear fission in detail. We will look at two types of fission, namely spontaneous fission and neutron-induced fission. Afterwards, we will see how these fission reactions can cause a chain reaction of further fission reactions, and then explore how these chain reactions can be controlled in nuclear reactors. Nuclear fission is a reaction where a massive nucleus splits into two lighter nuclei. There are two types of fission, spontaneous and neutron-induced fission. In spontaneous fission, the massive nuclei will split into smaller nuclei without any external triggers. For example, uranium-238 can undergo spontaneous fission to split into xenon-140, strontium-95, and free neutrons. The resulting nuclei are called fission fragments. This reaction will happen at random, but it is typically very rare for nuclei to undergo this type of fission. Instead, fission can be deliberately induced in nuclei by using slow-moving neutrons. Here, a slow-moving neutron will be absorbed by the massive nucleus, which causes it to be unstable and split into two fission fragments along with more neutrons. In this example, when a neutron is absorbed by a uranium-235 nucleus, it becomes uranium-236, which is very unstable. This will undergo fission and can split into barium-144 and krypton-89, along with free neutrons. Note that the fission products shown in the fissions on this slide are just two of the many possible pairs of products from uranium-236, and the number of neutrons released can also vary as a result. Energy is released in a fission reaction when the total energy that is released from the formation of two daughter nuclei is greater than the energy required to pull the original nucleus apart. To calculate this value, we can determine the difference in mass between the reactants and the fission products, and then use the mass-energy equivalence E equals mc squared. Using the rest masses of a neutron and uranium-235, the mass of reactants can be calculated as follows. Similarly, given the rest masses of barium-144 and krypton-89, the mass of fission products and free neutrons can also be determined. This then gives a mass defect of 0.186 atomic mass units, or U. From the data booklet, 1 U of mass is equivalent to 931.5 MeVs of energy. So using the mass-energy equivalence, we find that 173 MeVs of energy is released from one fission reaction of uranium-235. This is to be expected, as if we revisit the binding energy per nucleon curve, we see that uranium-235 has a lower binding energy per nucleon compared to both barium-144 and krypton-89, and so fission of uranium-235 results in an overall decrease in mass and a release of energy. We can also note that nuclei located to the left of iron-56 will not release energy by fission, because the heavier parent nuclei will often have a higher binding energy per nucleon compared to the lighter nuclei that would be formed. Notice how this particular neutron-induced fission of uranium-235 releases around 173 MeVs of energy and emits 3 fast-moving neutrons. These speeds are usually too fast to induce further fission, so a material called a moderator is used to reduce the speed of these neutrons. Materials commonly used for moderators include water and graphite. When these neutrons are slowed down, they are more likely to induce further fission in other nuclei, thus releasing more energy and more neutrons. But some of these emitted neutrons may end up getting absorbed without causing fission, or move without interacting with any nuclei. If the neutrons emitted from a fission reaction can induce at least one more fission reaction, then this process becomes self-sustaining and is known as a chain reaction. But as we can see, the number of fissions and the energy released will grow exponentially if the number of emitted neutrons is not controlled. In a nuclear reactor, chain reactions are controlled using control rods, often made of boron or cadmium. These rods can be inserted into a nuclear reactor and will absorb neutrons that collide with the rod. This will reduce the number of neutrons that can go on to induce further fission, and the rods can be raised and lowered to control the chain reaction. Chain reactions are used to keep a reactor running. In one type of nuclear reactor, cold water is used as the moderator in the reactor, and the energy released from fission reactions heats up the water. This heated water is then transferred to a heat exchanger, where heat is then delivered to a separate water system, where it generates steam, which goes on to drive a turbine system that generates electricity. There are safety issues related to nuclear reactors, however. The various fission fragments are radioactive and can have very long half-lives, while the emitted neutrons can also be significant health hazards. So shielding is used to protect people by surrounding the nuclear reactor with a steel and concrete barrier that absorbs and reflects these radiations. In addition, the radioactive nuclear waste will be stored and secured underground in strong containers, in such a way that they will be kept secure for thousands of years. We will now provide a final summary of the key understandings from this video. We saw that some nuclei can undergo spontaneous fission, whereby a nucleus can split into lighter nuclei and emit neutrons without any external triggers, but this is a rare type of fission. The more common type of fission is neutron-induced fission, where a heavy nucleus absorbs a slow-moving neutron, which can cause fission to occur. If a neutron emitted by fission goes on to cause another fission reaction, this process is known as a chain reaction. This is the basis of how a nuclear reactor generates power through the use of moderators, control rods, and heat exchangers. This now concludes our video on nuclear fission. Thank you for watching.